So far, we had looked at a variety of graph-based algorithms, including the graph traversal algorithms such as DFS and BFS. And we also looked at how to perform the shortest path algorithm and the Dijkstra's algorithm. So now we will shift our focus to yet another problem in a graph-based algorithm, which is widely known as the minimum spanning tree. So to get started, we will first recall our memory to define the difference between tree and a graph. A tree is a specialized case of a graph, and this graph should be connected with no circuits and self loops. So a circuit is where we said there could be a loop in the graph itself. Like for example, if you have a graph G that has a circuit here, as you can see, which is a loop there, um, then it's no longer a tree. And it should also have no self loop, which means it is looping within itself, right? So that's again not possible in a tree, whereas a graph could have both of those properties. And there should be only one path between any two vertices, right? So for example, if you would have this in a path between these two nodes, then you cannot have a path such as this one, which again ends up in a circuit there, which is going to make it a cyclic behavior in that graph. This is not allowed as well, right? So this is not allowed, and this is not a tree. If we have more than one path, if we call this path P1, we cannot have P2 that leads to the same vertex. And a tree does not contain any loops, as we talked about, and it is a minimally connected graph. Whereas a graph can have a loop, it can have any number of paths, and then it is simply, as you may know, that it has a vertices, edges, and a set representing relationship between vertices and edges. So what is a minimum spanning tree? Let us formally define this. Then we will look at one application of such a minimum spanning tree, and then we will look at an example. Later we will look at the algorithm. We will analyze that, and towards the end we will take up an activity to practice this algorithm. So first we are given with a graph G with a connected undirected weighted graph, right? So G is a connected undirected weighted graph where V is the set of vertices, E is set of edges. Each edge E, small a or lowercase e element of capital E, has a non-negative weight. So we are trying to find a subset T that's element of E, and again E is the set of all edges in that graph, right? So we are trying to find a subset of that uppercase E, which is again the list of edges there, such that all the vertices remain connected when only the edges in T are used, right? So we are trying to use only the edges in T, and then we want to make sure that it's still connected. And the sum of weight of edges in T are as small as possible, right? So we are trying to minimize. The goal is to minimize the weight of edges in T. That is our goal for this particular problem here, right? And again, we want to make sure it's connected as well, right? So that's a bottom line assumption that we take, that the graph should still be connected, or the subset graph should also be connected, right? So where can this be applied, this particular problem? So let's say we have a list of friends, right? Ross, Monica, Chandler, so on, Rachel, Joy, right? Um, let's say each of these friends are represented as the vertex in this graph, and then the edge has a weight. Let's say I pick 10, and this one is 20, and let's say I pick I pick 120 here, right? So the edge weight here that we are adding to this graph is simply the distance between those two friends, right? So the distance in miles, let's say. So the goal here is, let us say someone, Mark, would want to visit all his friends, right? And he wants to minimize his spending for the gas, right? So basically he's driving, to meet all his friends, but he wants to take the path so as to make sure that he minimizes the gas spendings, right? Um, so this is where we have the MST. If we can somehow derive a subset of this graph G, and if we call that as T, right, such that the sum of all the edges would be as small as possible. If we could do that, then Mark can simply take that particular graph or the so-called minimum spanning tree, and he can start visiting all his friends, um, and he will be basically having the minimum gas spendings, right, in that way. So how can we solve such a MST problem? There are two proposed algorithms, the Kruskals algorithm and the Prim's algorithm. And we will firstly look at the Kruskals algorithm. And let's pick an example here. Let's say we are given with this graph G, again connected, undirected, weighted graph. So we simply pick two lists here. One is for edge. I'm going to call this as an edge set. And the other one is the subset of this edge set, T. So let's call this a subset. So you can see that the edge set has all the edges sorted in an increasing order. So it is sorted in increasing order, right? So you can see 1, 2 is the lowest edge weight, then 2, 3, and then you have 3, 4. So if you have an edge weight that is same, then you can simply randomly pick any one of those edge weight, right? So here we are picking 3, 4, then we pick 0, 1, then 3, 1, and then you can see it's 0, 3, finally 0, 4. So we arrange them in a increasing order by doing the sorting. So in order to sort, we could simply pick any of the best algorithms, sorting algorithm that we had talked about in the past. So let's say we pick the merge sort. So it's going to be n log n, and in this case, because n is the edges, the number of edges that we are trying to sort, so we could simply say that it's big O of E log E. Right? So the sorting procedure takes big O of E log E. Right? And we will analyze that furthermore. We will come back to this point in a little bit. But for now, we understand that we are going to take all the edges in the graph and we are going to sort it in increasing order, right? And the next step here is we pick the minimum one or the lowest one in that edge set, which is 1, 2, and we add that to that subset T. The condition for adding it to subset T is that every time you add an edge to T, you want to make sure there is no cycle. If there is a cycle, then it's no longer a tree, and thereby you cannot add that edge to your subset T. So adding 1 2 did not have any lead to any cycle at this point, so thereby we simply add 1 2, right? So the next one we have is 2 3. And keep in mind, once you added a particular edge to T, you simply remove that from your edge set, right? So 1 2 has gone away now. So the next smallest one, or the lowest edge weight, is 2 3. Again, you're adding 2 3 to your subset T because there is no real cycle yet, right? So 2 3 is added. And then the same thing is done for 3 4 is added. And keep in mind, 2 3 we just take it out of that edge set, and 3 4 we took it out as well, right? And we added that to the T here. You see how that MST is slowly building there, right? So this is the spanning tree, as you can see right here. The spanning tree is slowly getting formulated, right? So the next one in the sequence would be 0 1. So we simply add 0 1 to that subset T because it didn't lead us to any cycle yet, right? So let's look at 3 1. 3 1 is right here, right? If I added 3 1, then it will simply lead to a cycle right here, you see. So 1 2 and 3 would lead to a cycle. We don't want to do that. If there is a cycle, if an edge would lead to a cycle, then we don't add that to our T. We simply remove that from the edge set. And then you have 0 3 as the next one. Again, the same problem. If I add 0 3, then it will lead to a cycle here, as you can see. 0 1 1 2 2 3 and 3 0. We don't want to do that, right? So we simply remove that. And finally you have 0 4. Again, same reason. If you add 0 4, it will lead to a cycle, so we simply remove 0 4. So you can see the number of edges in T would be, total number is V minus 1, meaning the total number of vertices, where capital V is number of vertices, minus 1. So in this graph, you can see that there are 5 vertices, right? 1, 2, 3, 4, 5. So the number of edges in T would be 5 minus 1, which is 4, right? According to the Kruskals algorithm, we say that the number of edges in our minimum spanning tree, or the capital T, would be total number of edges, total number of vertices V minus 1, right? 1 less than the number of vertices. So that's going to be our total number of edges. So the final MST here, you could see that it's 0 1 1 2 2 3 3 4, and the cost here is going to be 4 plus 2 4. Again, I'm counting 3 plus 1, and then you have 3, which sums up to a total cost of 9. So let us say that if we would assume that these are the 5 friends, and Mark is trying to visit all 5 friends, then he could simply visit all 5 friends by spending gas for 9 miles in total, right? So that's the idea here, is that we want to visit all vertices in the cheapest in cost, and the cost here refers to the edge weight, right? So the formal algorithm for Kruskals is we are given with a graph G, right? With capital V is going to be the vertices, uppercase E is for the edges, and the output here is we are trying to find a minimum spanning tree. T is the subset of that edge set, right? So we initialize t to be empty, the first step. Then we sort the edges in E in an increasing order, right? Then we run a while loop, and this while loop is run if while E is not empty and t is less than v minus 1, right? As long as t is less than v minus 1, we go inside, we take the next minimum edge, and then we check. If E does not create a cycle in T, then we add that edge to T. And then we remove E from capital E, right? So this particular edge is removed from the set of edges. And then again, you go back to the while loop and you run that condition again. In terms of time complexity, as we said earlier, the sorting procedure takes big of E log E. And this while loop, as you can see, the maximum time that this while loop can run would be till that E is empty, right? So meaning it's going to be big of E is the maximum or the worst case running time for that while loop, right? Because it's going to run all the way until all the edges are removed from that set E, right? So which means it's going to be big of E in the worst case. So you can simply do the time complexity analysis by doing big of E log E, which is for the sorting procedure, and then the while loop is big of E. So thereby this is going to be big of E log E, right? And this is a much smaller one compared to E log E. So we simply get rid of that for our asymptotic big O notation, and thereby the time complexity is going to be big of log E. So we will take up one tryout exercise for today, is that given this graph G, we want to find the minimum spanning tree for this particular graph, right? So please make sure that you include your E, T, and your MST in your solution, and post your solution in our general channel so as to make sure that we practice how this algorithm works and to also get the participation credits. So the next step for us would be to investigate on Prim's algorithm, which is another MST algorithm. Then we will look at one or two string algorithms as time permits this semester. And the reading assignment is based on section 4.3 in our textbook in Sedgwick. If there are any questions, feel free to ask. Okay? All right. Thanks for listening to this video.